I don't. There isn't one in here. Does anyone have a pencil sharpener? I don't know. Alright, are there any questions here on any of the homework? You guys all good with this? It's relatively basic stuff, but alright, good. So, what we're going to do is real briefly review partial sums of geometric sequences and series, and then look at infinite ones, and then an application, and after that, that's it for sections 1 through 3. Let me just point out the formulas that we've had, and one of these we will have today, okay, but these 5 formulas, the general definition for an arithmetic sequence, a sub n equals d times n minus 1 plus a sub 1. The partial sum of an arithmetic sequence, n over 2 times a sub 1 plus a sub n. And then the geometric sequence formulas. The general term definition is a sub n equals a sub 1 times r to the n minus 1. And then the sum of a finite series we looked at on Friday, s sub n equals a sub 1 times 1 minus r to the n over 1 minus r. And then what we'll see today, the sum of an infinite geometric, which we don't always put the infinity symbol there, but you can, if you just see an s, that's understood to be the sum of the entire series. And all series are infinite. So that's a sub 1 over 1 minus r. Right, so make sure that you know those, can use those, and we'll practice that more today. Yes?
Do we have the equation for combinations and permutation?
Not for this. The final test, which is a week from tomorrow, we're going to cover the last 2 sections the rest of this week. So after the quiz tomorrow, Thursday, and then Thursday, Friday, and Monday, and then your test will be, well, for you guys, Tuesday, Fusion Day. Yes?
So the final test will be just chapter 8, right?
Just chapter 8, yeah. So it's not a cumulative trimester exam or anything like that. So,
Thank you.
Amanda?
And so we should have these equations memorized.
Yes. Yes. So, and I've been telling you that along the way, but just wanted to reiterate that these are formulas you need to actually know. So, as we look at the geometric sequences and series, the partial sums, remember we looked at here when we have the sum of the first 12 terms, we're using this formula here. A sub 1 is 4 because we plugged 1 in. Or I'm sorry, we don't plug 1 in. We look at that term in front of the r to the n power, okay? And then we have the rest of our formula here, 1 minus 0.3 to the 12th over 1 minus 0.3, and we get 1.714. Then we saw a situation where we don't have it starting at 1, we have it starting at 0. And we said that the 2 ways that you could handle that are to actually plug in 0 and see what you get. You get that 4, okay? Which, I just realized, this should be
1.2.
Yeah, this should be 1.2. It's 4 over 0.3. Sorry. That equals 1.714. Okay? And that's 1.2. Okay. Alright. It's a sub 1, so you plug in 1 and 4 times 0.3. Sorry, 4 times 0.3 is 1.2. Then if it doesn't start at 1, you can either adjust your limits Here we're adding 1 to each limit, so we have to subtract 1 from the n. Or you can just plug in 0, figure out what that first term would be, and then add the rest of it. Okay? We add the rest of it, which we had just figured out, and we got the 5.714. Okay? So that's where we had left off on Friday. Was finding the sum of the finite geometric series. Okay? So just for a little bit of practice, let's try one here. Let's say we have the sum from I equals 1 to 10 of, let's go with a 3 times 1/2 to the I power.
Those are those are problems like for this quiz, right?
Yeah. And it really doesn't matter if we're using I or n, just whatever variable happens to be there, you're plugging values in. Okay? So, what would the sum from 1 to 10 of 3 times 1/2 to the n power be? Okay. And this is also known as S sub 10, the 10th partial sum. Okay? So using our formula, a sub 1 times 1 minus r to the n over 1 minus r, go ahead and find our sum.
R is what?
R is your common ratio.
Oh,
So what is that in this case?
3.
No. 1/2. The 1/2. Okay. A sub 1, you're just plugging in 1. So 3 times 1/2 be 1.5. Oh, you can round it to like two decimal places.
2.
Like, yeah, that 2 would be fine.
3.989. So 3.
2.989,
No, it's 2.997.
997. Okay. If it's something like that,
So
go
that's
ahead
three.
and rather than just making it 3, go ahead and show the decimals.
So we'll just do that.
Yeah. Okay. So 1 minus 1/2 to the 10th. 1/2 to the 10th is really small. It's like 1/128th, I think, or 1/1024th. Sorry. 1/1024th. So that's what you're subtracting from 1. Okay. This is 1.5 divided by 1/2, which is 3. So 3 times almost 1 should be almost 3, right? So it makes sense. Yes, Ellie?
Why is it 1.5 not 3?
Because you have to actually plug in the 1. So you have to actually multiply it that first time. Alright, so everyone with us on the finite geometric series?
Yeah.
Everyone understand? Okay. Is anyone not getting the 2.997? Alright, good. Alright, so let's look at infinite series. Okay? Infinite geometric series. As we've talked about in the past, most infinite series, or sequences I should say, just continue to get bigger and bigger and bigger, or further and further into the negatives. But when you add those terms up, it's going to either approach infinity or negative infinity. Okay? Yes?
What is a series and what's a sequence?
A sequence is just a list of terms that have a relationship somehow. A series is when you add up those terms.
So why do we say the sum of the series? Isn't that kind of redundant?
It kind of is,
Okay.
but
To make it, okay.
yeah. So here we have an infinite series. Like I said, usually when we have a series, if it goes infinitely, then it's either going to go to positive infinity or negative infinity. But as we saw with the 1/3, remember we had the sequence 3 over 10 to the n power. And it was 3/10 plus 3/100 plus 3,000 plus 3/10,000 and so on. It was just 0.33333333 once we added it, and it kept going. That was 1/3. So we saw how in that case an infinite series did come out to an exact value. Okay, infinity is not an exact value, but here in a particular instance, we can find the sum of an infinite geometric series. And what's the key part here? As you read this, the key thing that makes it so that we can find the sum.
Infinite?
What has to be less than 1? The common ratio, the absolute value of the common ratio has to be less than 1. That's the key thing right here. If your common ratio is 2, you can't find the sum of the infinite series. If it's -2, you can't find the sum of the infinite series. It has to be less than 1. So you have to have something like a 0.3. Okay? Or, like in this one, a 1/2. If we took those infinitely, we could find the sum of the infinite series.
Can we do less than 0? Like greater than -1?
It can be. It can be. And we'll look at what happens. Now, the reason why this works is because we're dealing with an exponential. And you guys, when we graphed the exponentials, okay, when that thing that we were raising to a power was bigger than 1, our exponential looked like this, right? This would be like 2 to the x, or 4 to the x, or whatever. However, when that, whatever you were raising to the x power was a fraction, like a 1/2 to the x, it ended up being like this, ended up decaying, and you notice you had this horizontal asymptote on the x-axis. So this value, if you think of it in terms of our series now, here's where n is 0, which isn't part of the series, but here's n equals 1, n equals 2, n equals 3, n equals 4, 5, 6, 7, and so on. As n gets bigger and bigger, what's the value of our terms approaching? 0, okay? Now, there is a proof out there, I've seen it, I don't remember it, okay? But when this happens, even though it never actually reaches 0, we can actually find the exact value of the sum, okay? And that's where this formula comes from, okay? So this is actually a pretty nice formula. It's pretty simple. It's just a sub 1 over 1 minus r. Okay, so when can we find the sum of an infinite series? When the common ratio has an absolute value less than 1. Right, so let's go back and take a look at this one. Okay, this is similar to one we've seen in the past. Notice on this one, we have n equal to 1. Instead of I equal to 0, we've got it equal to 1. Because we're going to infinity, it doesn't make a difference. Okay? So you don't need to worry, some of them are equal to 0, some are equal to 1. It doesn't make a difference. We could even rewrite this. Because you have the n minus 1, we could write this as the sum of n equals 0 to infinity plus 1 is still infinity. Or I should say infinity minus 1 is still infinity. Of 0.6 to the n. If you wanted to rewrite it so it matches our formula exactly, you can, but it actually makes no difference mathematically.
Is it 10? Is it 10?
I think so.
In an infinite
Zero to
series,
one.
you always see the number multiplying r is a sub 1.
Yes. Yes. Okay. And that might be the only difference there. Okay. So here what we have a sub 1, which if you plug in 1 here, whether you plugged it in here or here, both of them are going to give you 0.6 to the 0 power, so that's just 1, times 4 is 4. So I have 4 over, and then you have a 1 minus r, so 1 minus the 0.6. Okay?
4.4.
Yeah, 4 over 0.4, which equals 10. So this series will equal 10. Are there any questions about how we found that? How we used our formula?
So quizzes, that's what it's basically. Just plugging
Well,
in
that's one
numbers and
aspect of it. Yeah. Alright. Let's try another one. This is one that, just looking at it, you could probably write down. What's this going to add up to? 3 plus 0.3 plus 0.03 plus... It's going to be, 3 and 1/3. Alright, but let's see how that works using our formula. Okay? First of all, we need a sub 1, right? Because it's a sub 1 over 1 minus r. So, a sub 1 is 3. What's r? 110. Okay? You'll notice each time we're dividing by 10.
I know it's obvious here, but what was the equation that you do to find r again?
You would just take this divided by the one previous.
Okay.
Okay? Good question. Yeah, 0.3 divided by 3 would give you a 0.1. And that's consistent. 0.03 divided by 0.3 would give you a 0.1. So, right. So now we have the two values we need, so we can just plug them in. 3 minus 1 minus 0.1, so that's 3 over 0.9. And that's going to be 10 over 9, alright?
3 and a third.
So 3 and 1/3. 10 over 3, which would give you 3 and 1/3.
I have a question.
Mhm.
Like for geometry, we have like two different sum of equation, but why the arithmetic only have one to sum of?
Well, that's a good question. On arithmetic, remember we used the term here converging because it's approaching 0. We would call this a converging sequence. Okay? And geometric ones can be divergent, which means they're not approaching a particular value. They're just going off into infinity. Or it's also possible that they're bouncing back and forth between positive and negative infinity. Okay? But when they converge, we can find the sum. Arithmetic sequences will always either approach positive infinity or negative infinity. Because you have that common difference. They're constantly going to be either increasing or decreasing. Either way, it's going to be infinite in its value. Okay?
So like for geometry, if you ask us to find the infinity series, we use the second equation.
Yes, we
But
would
for
use that.
arithmetic, if it's infinity, also use the second equation here.
Well, if it's arithmetic and it's an infinite series, you know that it's either positive infinity or negative infinity. Those are the only two possibilities.
Oh, yeah.
Because you're either, think arithmetic is linear, right? So you're either going up forever or you're going down forever, depending on whether your common difference is positive or negative. So, yeah, Alex?
Okay, I have two questions. First, on infinite series, if you were to ever ask us one where r was greater than 1, would we just write infinity?
You could just say, yeah, you just look at it, is it getting infinitely big or infinitely small, and then you could just say it positive or negative infinity. Yeah.
Can I use the question?
Is the sum of infinite series an exact number?
It is. This one is exactly 10, and this one's exactly 3 1/3.
Yeah, I understand the 3 1/3, but how is 10? I mean, is never reach the 0, but why there's an exact number?
You're getting into kind of the proof
Yeah.
of the formula,
Yeah.
and honestly, I don't remember the proof of the formula right now. It is something, if you're interested in seeing where this formula came from, I'm sure if you Googled it or something, you could easily find it. So, yeah. Alright, let's try one more here, infinite. Someone give me an example of a geometric sequence that we would be able to find the sum of.
4 times negative 0.2.
Okay. Find the sum. I shouldn't put equals there. I should put the sum from n equals 1 to infinity. Or actually it should be 0 to infinity. Okay. Okay. Now this one's interesting. If you look at the terms of this sequence, one's going to be positive, one's going to be negative, then positive, then negative, then positive, then negative. Okay? We would have 4, and then 4 times negative 0.2 is going to be a negative 0.8. And then times a negative 0.2 again would be a positive 0.16. And then a negative 0.32, and then a positive 0.032, yeah, 0.032.
Positive.
And then 0.064, yeah, and so on. And now notice, here's where you kind of see the converging. See how even in the first 5 terms we're getting close to 0. But it's kind of interesting because if this is my x-axis, look at what's happening. I'm up here at 4, then I'm at negative 0.8, then I'm at positive 0.16, then a negative 0.3032, then a positive, and what's going to happen?
How do you graph that?
Like that. Because remember, it's a sequence; it's not continuous. So it's just points, boom, 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 boom. And that's what it would look like.
The first term is 4, right?
The first term would be 4.
But
And then the second term is negative 0.8. So it's jumping back and forth, but notice it's still converging on 0.
But like the n equals 0 is the first term of the n. I say like n should be 1, then it's the first term, I think.
Yeah, we need to.
And I equals 0 then.
Yeah, equals 0 if I is not. The first term should be n, right? And like a1 is the first term, and
Hang on. A sub 1 is the first term.
Yeah.
Okay, so we're going from I equals 0, alright? So this is going to be our a sub 1 right there. So we would have 4 over 1 minus a negative 0.2. Okay? Point. I got my. There we go. So now it's 1.2, 4 divided by 1.2, and that's going to be 3 1/3.
It makes sense.
Okay?
Just by looking.
Okay. So it makes sense that it's going to be probably less than 4 because we have 4, but then we're subtracting and adding, subtracting, adding, subtracting, and so on. Yes?
So if 4 is A1 and like that position in the equation is always A1, why did you sometimes like plug in 1 for n to find A1?
Well, it's what we've got to do. If you look at the formula, when it's from I equals 0, okay, whatever this number is in front of the R is going to be your A1. Okay? When we had this, okay, we had to convert it, and then that was our A1. Okay? Where it might be a little different is if you had it starting at 1, but then this was just a normal n. Okay, you might have to do some working to figure out what A1 is.
So
Right.
when do you have to convert it?
Only if it's not starting at 0.
So if it starts at 1, I can't plug in 1 for n? That's
Well, no, you can because it ends up being the same here. Because if I plug in 0, that's 0.6 to the 0 power. If I plug in a 1 over here, it's 1 minus 1 is 0. It's still 0.6 to the 0
will it
power.
always work out, not just in that example, but in others also? Like what if it said it's n equals 1, but then instead of saying n minus 1, it's like n minus 3?
Then you'd have to
Adjust
kind of
it.
work with it a little bit.
With n equals 2, you would just do n minus 2 instead, right?
Wait, what are you asking?
Like if n was equal to 2 instead of 1, you
Mm-hmm.
would just do n minus 2 instead of n minus 1, right?
Hang on, let me. Hang on. So you're saying, you're asking, if I was getting the sum from I equals 2,
Yeah, to infinity. And say it was 4 times 0.6.
everyone else be quiet,
And you
please.
just do n minus 2, so the exponent would be n minus 2 instead, right?
Okay,
That-
yeah, that would be the same thing as well, because I could subtract 2 from here and add 2 up there. The place where it might get a little bit tricky is, like if this were just n, okay? Then what we would need to do, we need to get this to look like this. Starting at 0 and having r just to the n power, or the I power, or whatever it is. So if it were like this, I would need to get this to be 0 by subtracting 2. Okay? So that would be 0, but then in order to compensate, I would have to add 2 up here. But that's where the a sub 1 you have to do a little work with. Okay? Now you could do this a couple of different ways. Probably the best way would be, we want it to be 0.6 to the n power. So that means we have a 0.6 to the n times a 0.6 squared. Okay? So 0.6 squared times the 4.
And then you put that in front.
Alright, and then that's what's going in front, okay? that's what's going in front. So we have the sum from I equals 0 to infinity of whatever 0.36 times 4, 36 times 4, 120, 144. So it'd be 1.44. Okay, and that would be it. Okay, now we can use our formula. Yes?
Can't you just plug in like whatever I is for n to find A1? Like for the example underneath that you did,
Yeah.
to find A1, can't you just plug in 1 for n instead of like changing?
Well, here's the thing. What this is saying, here, yeah, you can. Okay. This one, I'm trying to remember what it was. It was I equal 2. If you plugged in 1, 4 times 0.6 would have been, what, 2.4?
Yeah.
Okay. So what I would do is look at the formula that you're using, okay? That tells you everything you need to, that tells you exactly the form that you want to be in, okay? And it's telling you that whatever that number is A sub 1, okay?
But
So-
like for the other problem that we did when Ellie asked why the first term was 1.5 instead of 3.
Are you talking about back here?
Yeah.
Okay. This one, because it's a finite one, it's just working a little differently. Okay.
So for finite series, you have to find A1 first. It's not
Yeah.
a term right there.
Yeah. Okay. So. All right. Yeah.
Does R have to be greater than -1? It can be.
Yes. Yeah, and notice in the formula, it's the absolute value of R has to be less than 1. So yeah, it's something between -1 and +1, but it's not 0, obviously. So, all right, let's take a quick look at an example of something where this the sum of a finite geometric series can be used. We've looked at compound interest before, okay? The thing is, every example we were looking at with compound interest, it was a situation where what we did was we put money in and we just let it sit there. Okay? But now, what we're going to look at is a situation where we're making a monthly deposit. Okay? And this is the type of thing you might be doing, like, for instance, if you're working and then you're setting money aside every month into like your savings account or something like that. You're putting aside money every month. Or for instance, when you start saving for retirement, okay, you might have, if your company gives you a 401k or a 403b or something like that, you can have a certain amount of money taken out of every paycheck. So you're adding to it consistently. All right? Well, what that's called is an increasing annuity. And it's kind of interesting. There are calculators online that you can find for, how much will this be worth. But let's just look at an example of this and see how it relates to a geometric sequence. Okay? It says a deposit of $50 is made on the first day of each month in a savings account that pays 6% compounded monthly. What's the balance at the end of 2 years?
This sounds like quite a problem.
Okay, so
Okay. then I've given you a little bit of a tip. Okay, we're going to look at them in reverse order. So it's 2 years. So the last deposit
N equals 24.
is the 24th month. Okay, 24th month, that's going to be our A sub 1. Alright? We're going to look at these from the last to the beginning.
Oh.
Okay? So think about this.
Oh, we're gonna, oh,
That last deposit we make is $50 and it's earning 6% annual interest, right? If you're given a percent, that's annual. Now, if it's annual, how much are we making in 1 month?
cool, alright, the 12%.
Yeah, that's a yearly rate. So for monthly,
It says compounded month.
Yeah, that's what
Yeah,
I'm
it's
confused about. It
compound.
says compound.
well, we'll get to the compounding part in a second.
Oh.
The compounding is where the geometric sequence comes from. Okay? We'll get to that. But we need to look at the reason why we're getting a monthly rate, 6% divided by 12, we're making 0.5% interest every month. Okay? The reason why we have to do that is because our deposits are monthly. So we're looking at this month by month by month, and what we're going to do is create a geometric sequence with 24 terms. Okay? 24 months. So this first one is going to earn 0.5%. So how would we calculate how much we'll have after a month?
50 times 0.05 or 0.05.
That'll be the interest.
1 plus 0.05.
Okay. 1 plus the 0.005. So 1.005. That'll give us the amount that $50 is worth after that last month. Does that make sense? And I think this was 50.25.
So why do we do the 0.5%?
Because in 1 month, if you're making 6% on a year,
We're making 6% on a month.
no, the 6% annual interest rate
Okay.
is compounding monthly. Okay?
Got
Anytime you're given an interest rate like this, it's going to be a yearly rate, annual rate.
So you're technically only getting 0.5% a month
Mm-hmm.
for a total of 6%.
Yes.
Okay. So
Yes.
if you left it in there, you gained 6% total. No,
At
the
you
end-
at
you
the
gain
end of the
6%. You like but not necessarily because after the first month, the second month you gain.
You're gaining 0.5% on
Okay.
this, and then 0.5% on that, and then 0.5%. That's the compounding part that comes
Got
in. Okay. Yes.
Why is it 1.005?
Because the 1 is the original $50, the 0.005 is the interest you're adding on to that. So the interest was 25 cents. The 50 is the original amount, okay? So, there we have our first term. Now, how are we going to figure out our second term?
You're gonna
compound.
times.
Or You're gonna
Multiply
compound
the
You're gonna multiply
50.25 by 1.005.
Okay, because if you think about it, it's going to grow by that much in 1 month, but this one got to grow for 2 months, right? So, yeah. Okay, I don't know what that is off the top of my head, but regardless, that's how we figured it out. So then the third from the last month. 50 times,
that number cubed.
yes. And so on. So, let's come down here to the very first month.
So it'll be 50 times 1.0 to the 24.
The first month is A sub 24. Okay. And here we're kind of defining N as how many months did this deposit have to earn interest. Okay, so this very first $50 that we put in there, it got to be multiplied by the 0.005
24 times.
24 times.
Oh, that makes
Okay,
sense.
Not really though.
it did.
So if you put $50 in there. Okay, yeah.
So 56, 37, 36.
Okay, so
I'm
Yeah.
really confused why the 24th month is ace of 1 and the first month is ace of 24.
because of how we're defining this number right here. That number right there is how many months does it earn interest? Okay. So our last deposit is only earning interest for 1 month. Our next to last deposit gets to earn interest for 2 months. Our very first deposit gets to earn interest for 24 months.
But aren't you
Okay.
adding $50 a month as well?
We are. And this is where the sum of the finite geometric sequence comes into play. Alright? Here's our a sub n. A sub n is a sub 1, the 50.25, times 1.005 to the
And
n minus 1. Okay?
yeah, because then the first time it's not getting any power.
Yeah.
Oh,
So what we're going to do, we're going to find the sum from I equals 1 to 24 of that. Okay? I'm just going to put a sub n. So what's our formula for that? It is
Ace of 1 times 1 minus r over
a sub 1, 50.25 times 1 minus the 1.005 to the 24th power,
Oh,
all over
1.
1 minus 1.005.
1,000.
Just makes sense.
Right? And then what? How much was that?
1,277.96.
Yeah, there we go. So, by putting $50 away every month and earning 6% interest on that, you end up depositing a total of $1,200. So you made $77.96 in interest. Okay, which doesn't seem like a lot, but think about it. For a lot of that time, you didn't have very much money in the account. Okay, and think about it. After 6 months, you only had $300 in the account. After the first year, you only had $600 in the account. So you didn't have a whole lot in there to earn interest. Okay, but
Thank you.
see ya.
I'll try.
So but that's how this relates. Okay, and that's just one application, obviously.
I don't think she's. Yeah, I said the same thing.
It's just one application. Is that
Will this be on the quiz tomorrow?
no?
No. Okay.
No.
Just-
Okay.
I'm still kind of confused.
But that's the idea of the increasing annuity. And it's just, guys, this is a situation where I hope you can, what we're doing here is we're drawing a connection between the exponential functions we looked at and the geometric sequences and series that we're looking at now. Okay? This was a situation where we had exponential growth. Okay? Think about other situations where we looked at exponential growth. We could figure out a cumulative amount over time. Okay? So, anyways.
Mr. Erickson,
Alright. Yes,
for the quiz tomorrow, do we need to know the combination formula and the permutation?
not for the quiz tomorrow. We're gonna use that more, in our last section on the binomial theorem.
Oh, yeah.
But we'll look at it then, but, so you'll need to know that. You're not gonna have to memorize the permutation one at all for right now,
Are
but,
we doing that deduction?
so, yes, we're gonna start that tomorrow after the quiz.
Wait, what's the
I haven't told that to
permutation?
my-
Alright, so, that's it, I've given you some to practice with, okay? We'll take some quick questions first of all. If you have some questions, but they must be ones that you've actually tried, okay? So, I'm not gonna take questions if you haven't bothered to try it, and then want just some extra practice before the quiz, okay? So try these, and take a look, see what you can do with them, and we'll be all set for tomorrow.